All right, so we're going to be looking on titration. I'm going to be answering some titration questions. So the purpose of a titration is to determine the concentration of a standard solution. So we're going to determine the concentration of a solution, using a standard solution. So we have a solution that we don't know its concentration, and we're going to use a solution of known concentration to determine the concentration of the solution. All right. So the standard solution goes in the burette, and the solution of unknown concentration that goes into the pipette, and we're going to use an indicator. The indicator is going to tell us when the whole neutralization process takes place. So we will have a color change of the indicator. Now, the standard solution, so remember, we pipette some, so the standard solution is standard solution goes into the burette. I pipette the solution of unknown concentration. I add some indicator there, right? And I will know the volume of the standard solution, which neutralized or react exactly with the amount of solution I have in my conical flask by seeing what volume of it causes my indicator to change color. So we'll have the initial, so the burette, we have a final reading from the burette, the initial reading from the burette, the final reading. So we're going to take final from initial, and we'll get the volume of solution used. The titration is repeated until we get identical volumes or volumes that differ by 0.1. Now, in order to determine the solution's concentration, we need to do a series of calculation. Now, your teacher may have taught you using statements, but this is a quick revision, so I'm not using the statements. I'm using only formulas, right? If you want to use the statements, that's fine. So the first calculation we're going to do is to calculate the average volume of standard solution used. Notice, if the volumes are identical, we will use the identical volumes, right? Or we are going to use volumes that differ by 0.1. But if all three values differ by 0.1, we're going to find the average of all three. Then we are going to calculate the number of moles of standard solution. To do that, we're going to say number of moles is equal to concentration of solution in moles per dm cube times volume. So if your concentration is not given in moles per dm cube, somewhere along the line, you'll have to convert from moles per dm cube to grams per dm cube. So to calculate the number of moles in the standard solution, we are saying it's the number of moles times the concentration in moles per dm cube times the volume, and the volume must be in dm cube. So our burette readings are usually in centimeters cube. So how do we move from centimeters cube to dm cube? We simply are going to divide the volume given in centimeters cube. So that's the volume we have up here, to convert that to dm cube by dividing by 1,000. Then we are going to write a balanced chemical equation for the reaction occurring between the solutions. This is the solution of known concentration and the solution of unknown concentration. Then we are going to write the mole ratio between the standard solution and the solution of unknown concentration. So the known goes first. So the mole ratio is simply the whole number in front of the chemicals in the balanced equation. All right, then we're going to calculate the number of moles of the unknown in the pipetted volume, that is in the 25 centimeters cube or whatever volume they give you. So although you're given a volume in this part of the question, you are not going to use the volume to answer the question. What you are going to use is, so the volume, so they're asking you to calculate the number of moles of the unknown in the pipetted volume, right? You are not using the volume. What you are going to be using to do this is the mole ratio. So the mole ratio between the standard solution and the unknown. So, and then the number of moles of the standard solution used. So you're going to use your mole ratio in step 4 and your answer to step 2, cross multiply to get the number of moles of the unknown. Now, when we're finished with that, we are going to calculate the concentration in moles per dm cube. This is where we use the volume. So whatever volume is given in step 5, we're going to say concentration is equal to number of moles divided by volume. So this volume that is in step 5, we are going to divide it, convert it to dm cube, and divide it by the number of moles. So then in a nutshell, that's how titration is done. We are going to be using this to answer some titration questions. Let me just make sure it's a titration question. This is where we are. So we're going to be doing a regular acid-base titration. So students, let me just zoom in a little bit. Why am I never do this for morning? So students were required to prepare So students were required to prepare a sample of normal salt produced when aqueous sodium hydroxide reacts with dilute sulfuric acid. Define the term normal salt. So a normal salt is a salt form when all the H plus ions from an acid is replaced by metal or ammonium ion. So normal salt is formed when all the H plus ions from an acid is replaced by metal or ammonium ions. So that's a normal salt. Identify one other type of salt that can be formed from the reaction between dilute sulfuric acid and aqueous sodium hydroxide. So there are 2 types of salt. We have normal salt, and the second type of salt would be your acidic salt. And although the question didn't ask for it, your acidic salt is formed when some. So where we have all here, all will be replaced by some. When some of the H plus ions from an acid is replaced by metal or ammonium ions, in case they had asked for that definition. A normal salt was produced by conducting a titration. The students were provided with a dilute solution of 4.9 grams per dm cube sulfuric acid. So when we read this, we are given the concentration of sulfuric acid, and the concentration is given in grams per dm cube. So we are going to make a note that this is our standard solution. So our standard solution is our sulfuric acid. Notice its concentration is not given in grams, in moles per dm cube. It's given in grams per dm cube. So at some point in the question, you're going to be asked to convert from grams per dm cube to moles per dm cube. You are given 5 grams of sodium hydroxide and screen methyl orange. They carried out the procedure outlined in Part A and B. The titration results for Part A are represented in Figure 1. Review the procedure in Part A for the preparation of the normal salts and answer the question that follows. Procedure: 5 grams of sodium hydroxide. Place 5 grams of sodium hydroxide solution into a conical flask and add distilled water to make 250 centimeters cube of the solution. Pipette 25 centimeters cube of sodium hydroxide. So this is the volume of the standard solution. This is the volume of the solution of unknown concentration that we're going to be using. Then we're going to add 2 drops of phenolphthalein indicator to the sodium hydroxide solution in the conical flask. Place the sulfuric acid in the burette and titrate the sodium hydroxide solution until the endpoint is reached. Then we are going to repeat steps 2 to 4 until consistent results are obtained. So again, we say consistent results are results with identical volumes, or volumes that are off by 0.1. So we're going to look to see where our volumes are increasing. So here we are moving from 0 to 1, so we are increasing downwards. After we figure out which direction we are increasing in, we are going to calculate each small values here on the scale. So we're going up by 1. So the difference between each of these lines that I underlined are 1 centimeters cube. And we're going to count the number of lines. So 0, the first line is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 divided by 10, we're going down by 0.1 centimeters cube. So now we're going to take an opportunity to read off these values. So we'll start with final first. So our final is here. So we start at 25. We're going down by 0.1. So 25, 25.1, 25.2, 25.3, 25.4. The bottom of the meniscus sits on 25.5. So 25, 25.5. And then your initial reading would be 0. So we start at 0, then this is 0 0.1, 0.2. So this would be 0, 0 0.1, 0.2, 0.3, 0.4, 0.5. So it's 0 0.5. Here we would have 37, 37.1, 37.2, and the bottom of the meniscus here sits on 37.3. Here we have 12, 12.1, the bottom of the meniscus sits on 12.2. Here we have where it sits on 40.5, and here 15.5. So I'm just gonna put these in so I can copy and paste. This is complete table 1 by using the reading shown in figure 1 on page 6. So we would have read them off already. So we can just put them in quick and fast. So we have 25.5, 0.5. To calculate the volume of acid used, we are going to subtract final minus initial. So that's going to be 25.0. Then now we look here, final for the second one is 37.3. Initial is 12.2. So 37.3 minus 12.2 gives me 25.1. Final reading for the last one is 40.5. Then I have 15.5. And then I have 25.0. All right, so notice in my tables, I have 2 identical volumes. So the 2 identical volumes I have are 25.0 and 25.0. Although 25.1 differs by 0.1, because I have 2 identical volumes, I'm going to be using my 2 identical volumes as the volume of acid used. Clear?
Yes.
So it is in the table, you indicate using an asterisk the titration volumes that would be used to calculate the average volume of the sulfuric acid. So using this and this. So because although they are the same values, because the question says calculate the average, we need to perform the calculation. So it is 25.0 plus 25.0 divided by 2, and my answer is 25.0 centimeters cubed. Clear? So here, let's go. It says in my notes that I must calculate the so the first calculation says calculate the average volume of the standard solution. So we did that. We have identical volumes. We use the identical volumes to do the calculations. All right, so we are complete the procedure for B by stating the steps required to obtain a dry sample of the normal salt. So from the titration, the information that the titration gives me is that 25 centimeters cube of NaOH will react with 25 centimeters cube of my H2SO4. Now, because I know the volume of sulfuric acid that is going to neutralize my NaOH, so the purpose of repeating the titration is to find out the volume of the acid of the standard solution that will neutralize the solution of unknown concentration, right? So I know it is 25. So I don't need an indicator. In order to prepare a dry sample of the salt, I cannot use an indicator. If I use the indicator, the salt is going to become impure, right? So we're pipetting the same procedure they used a while ago. Pipette 25 centimeters cube of sodium hydroxide solution and transfer the solution to a conical flask. Using the burette at volumes of sulfuric acid used to neutralize the base. So we're not using the indicator, right? Because we already know the volume of sulfuric acid which neutralized my sodium hydroxide. So I want to obtain dry sample of the salt. So when I add that, what am I going to do? So when I add that, when sodium hydroxide reacts with sulfuric acid, I'm going to get water and salt. So what I have now is water and salt in the mixture. I don't want the water. So in order to get rid of the water, what am I going to do? Evaporate the mixture. So I'm going to evaporate the mixture and wash and dry the salt crystals. So that's what I'm going to do. It's a balanced equation including state symbol for the formation of the normal salt from sulfuric acid and sodium hydroxide. So H2SO4, aqueous, all acids are aqueous, reacts with aqueous sodium hydroxide to form sodium sulfate. Now, we know it is a normal salt because this acid has 2 H plus ions. So if we look at this acid right here, we're seeing 2 H plus ions. Both H plus ions are replaced with sodium. So because both H plus ions are replaced with sodiums, we have a normal salt. So replace both of these H plus ions with sodium ions, so we prepare a normal salt. So we need to balance our equation. So I have 2H. All right, I don't balance H first. So I generally balance metal, the anion in the salt, then hydrogen, then oxygen. So the metal here is sodium. I have 1 on the left, 2 on the right. So I'm going to put 2 in front of sodium. My metals are balanced. My anion, which is the ending of the salt, is sulfate. I have one sulfate here, one sulfate there. That is balance. So now I need to balance my H's. I have 2H here. 2 times 1H is now 2H. So 2 plus 2H is 4 H's. In water, I have 2 H's. So what number multiplied by 2 gives me 4? So that number is a 2. So I'm going to go ahead and clean up this nicely. All right, so in terms of reacting, 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide to form 1 mole of sodium sulfate, 2 moles of water. So my known is my H2SO4. So 1 mole of sulfuric acid will react with 2 moles of sodium hydroxide. We'll need the mole ratio for some time later. So it says, calculate the number of moles of sulfuric acid used to neutralize the sodium hydroxide. So remember that this is going to be my standard solution. So sulfuric acid, I made a note, is my standard solution. So it says, calculate the number of moles of standard solution. Number of moles is concentration in moles per dm cube times volume in standard solution. So my volume, my concentration is not given in standard in moles per dm cube. It was given in grams per dm cube. So let's go back up to the question. And it told me that it was 4.9 grams per dm cube. So I'm going to convert from moles, from grams to moles. So I'm going to convert from 4.9 grams per dm cube to moles per dm cube. So this is what I'm going to do. Number of moles is equal to mass divided by molar mass. The mass given is 4.9. The molar mass given is 98. So the number of moles is going to be 0.5. 0.05, sorry. So the concentration is 0.05 moles per dm cube. So number of moles is equal to concentration times volume in dm cube. The volume of sulfuric acid I'm going to be used is the average volume of sulfuric acid I calculated in part 3 of the question here. So it's 25 centimeters cube. So the concentration is 0.05. I must convert the volume from centimeters cube to dm cube. So to convert from centimeters cube to dm cube, the volume in centimeters divided by the volume in the volume which is 1,000. Right? So this is me in this step where I have 25 over 1,000. This is where I'm converting from centimeters cube to dm cube. So my answer is 1.25 times 10 to the negative 3 moles. Calculate the mass of normal salt expected from the reaction. So this is not my standard titration question. So what it wants me to find is not the mass of the solution of not the concentration of sodium hydroxide solution. What it wants me to find is the mass of the salt. So here I am going to say, I will have to use the known and the unknown. So I'll come up here. I know the number of moles of sulfuric acid, and I want to know the number of moles of the normal salt that would form. So I'm going to start with my mole ratio between the known and the unknown. So they are 1-to-1 mole ratio. So 1 mole of H2SO4 reacts with or produces 1 mole of Na2SO4. Therefore, 1.25 mole of H2SO4 will react with X, and because it's a 1-to-1 mole ratio, X is going to be 1.25 times 10 to the 23. -3, sorry. So I'm not done yet. So this is the number of moles of Na2SO4 that is formed. But the question wants me to calculate the mass of the normal salt. So the mass is going to be number of moles is equal to mass over molar mass. So it's the number of moles multiplied by the molar mass. So I will calculate the molar mass for Na2SO4. 2 times the mass of sodium, 2 times 23, plus the mass of 1 sulfur plus the mass of 4 oxygen is equal to 142 gram per mole. So to convert that to mass, 1.25 times 10 to the -3 times the molar mass will give me my answer in grams. .18 grams. I round it off. I got 0.1775, so I round off to 0.18 grams. Let me know if we have any questions. The actual mass of salt obtained by the student was 0.9 grams. So theoretically, the student should have gotten 0.18 grams, but theoretically, they only got 0.9 grams. So just one possible reason for the difference in the expected mass of the salt obtained. So why is the mass less? Lost salts could have been lost during evaporation. So during evaporation, salt crystals split. So the salt forms the prop out of the solution. Some dissolved during washing. All right, so that's where we are at right there. Any questions? No? A student is asked to make a All right, a student is provided a standard solution of aqueous sodium hydroxide containing X grams of sodium hydroxide in 25 centimeters cube of the solution. In order to determine the mass of sodium hydroxide used, he titrated 25 centimeters portion of the solution using 0.025 moles per dm cube sulfuric acid. So the sulfuric acid is a standard solution. It's already given in dm cube, so I will not need to do that step where I convert from grams per dm cube to moles per dm cube. Right? Using a suitable indicator. So here are my burette readings. Again, I'm going down by 1. It's increasing from top to bottom, moving by 1. Count the spaces. 1, 0. The first one is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1 divided by 10 is equal to 0.1. So I'm going to be going down by 0.1. So my final titration reading for titration number 1, can we read it for me? Can somebody read it for me? 28 point what? Nobody?
Miss 4.
28.4. And the initial is 3 points.
3,
3.
All right. For titration number 2 was the final reading.
33.2,
33.2. 8 points.
2,
2. Last one. 29.8.
8,
8.
29.8, we say. And then last, the initial is what? This. What's that?
6.6.
6.6.
Okay. All right, so describe the process involved in preparing a standard solution of aqueous sodium hydroxide containing X grams in 250 centimeters cube solution. So the first thing we're going to do is to measure X grams. Using a analytical balance. Then we are going to transfer X grams to a clean burette. Add a small volume of distilled water in and dissolve I can say transfer the sodium hydroxide. Then we're going to pour the dissolved solution So I'm going to pour the dissolved solution into a 250 ml volumetric flask. Using a funnel. Then we're going to rinse the beaker with some more distilled water. Then we're going to rinse the funnel. So some amount of sodium hydroxide will be left in the beaker. So you're going to add some more distilled water to rinse the burette and pour into the conical flask, into the volumetric flask, sorry. When we're finished doing that, we are going to add more distilled water to the flask until add more distilled water to the flask until the graduation, until the water sits on the graduation mark. So that's how we prepare a standard solution. So to prepare a standard solution, you're going to measure accurately the mass of the solute that you want. And then depending on what volume of volumetric flask, depending on the volume of standard solution you're going to use, you'll have to use that specific volumetric flask. So because we're making a 250 centimeters cube, we are going to use a 250 centimeters cube or ml volumetric flask. So let's go. We're going to measure the X grams of sodium hydroxide accurately using a balance. Then we're going to transfer sodium hydroxide to a clean, why may I have beer here? So I'm say beaker. No, watch me now. So a clean beaker and add a small volume of distilled water and dissolve. And then we are going to pour the dissolved solution into 250 ml volumetric flask using a funnel. Then we're going to rinse the beaker with some distilled water and pour it into the conical in the volumetric flask. Then we're going to add more distilled water to the flask until the water mark sits on the graduation mark. So that's how I would prepare my standard solution. So 3 marks. Now it's asking me to put in my titration values. We had already read them off. So this is 28.4, 3.3. So my volume use is 25.1. Over on this side, I have 33.2. Final is 8.2. So I am using here 25.0. Please check my calculation to make sure they are correct. Then I have 29.8, 29.8, and then I have my 6.6. So the volume used here is going to be 23.2. Clear? Those are correct, right?
Yes, miss.
All right, so the next question is going to be using the best two values from the table state, the average volume of acid used in centimeters cube. So what two values will I use?
25.1 and 25.0.
Which one? I'll use
25.
these two values, 25.1 and 25.0, because they're off by only 0.1. Identify a suitable indicator for titrating sodium hydroxide and sulfuric acid. I am going to be using it's phenolphthalein. I think that's how it's spelled. So I'm going to be using phenolphthalein. So my endpoint. So in my pipette, I have a base. So my phenolphthalein in base is going to be pink. And when acid is added to it, it turns from pink to colorless. So that's going to, so a color change from pink to colorless will determine, so phenolphthalein will turn from pink to colorless. So whenever it reaches colorless, then I will know that my endpoint is there. Write a balanced chemical equation for the reaction that occurs when sodium hydroxide solution reacts with dilute sulfuric acid. So we have, anybody wants to give me that? Same equation we did a while ago. So H2SO4 aqueous plus 2 moles of NaOH aqueous produces Na2SO4 aqueous plus 2 water liquid. Using the data provided in table 1, calculate each of the following. The number of moles of sulfuric acid. So remember, sulfuric acid is my solution of known concentration. The concentration given is 0.025 moles. So number of moles of standard of solution is number of moles times concentration times volume. So it's going to be number of moles times concentration times volume. Volume must be in dm cube. So 0.025 mole multiplied by 25.05. That's in centimeters. To get it to dm cube, I must divide by 1,000. Ten to the negative 4 mole. So that's what I got. That's what I got. Calculate the number of moles of sodium hydroxide in 25 centimeters cube. Now the question says I must calculate the number of moles of the unknown in the pipetted volume. So I'm going to use the answer in step 4, which is the mole ratio between the standard solution and the unknown and the number of moles calculated in step 2. So I'm going to go ahead and do that. So from the equation, my known is 1 mole of H2SO4 reacts with 2 moles of NaOH. Therefore, 6.2625 times 10 to the negative 4 mole of H2SO4 will react with X. Now I cross multiply. So 6.2625 times 10 to the 4 multiplied by 2 is equal to 1x. So I'll just multiply my answer by 2. So I get 1.2525 times 10 to the negative 3rd mole of sodium hydroxide. Clear?
Yes, miss.
So it doesn't want me to find the concentration, it's giving me a volume. So what I'm going to do here is to say that in 25 centimeters cube, I have this number of moles. So therefore, 250 centimeters cube of X moles, so I'll cross multiply. So I have 25, 250 times 1.2525 times 10 to the negative 3 equals, and if you can hold on here, so. All right, let's put it here, 250 times 1.2525 times 10 to the negative 3 is equal to 25 times x. So 1x by itself, we're going to divide both sides by 25. So our answer is 1.2525 times 10 to the negative 2 mole. So we know that in 250 centimeters cube, I have 1.25 times 10 to the negative 2 moles of NaOH. So the next question is asking me to calculate the mass dissolved. So I have the number of moles dissolved, so I need to find the mass dissolved. Number of moles is equal to mass over molar mass. So I need to calculate the molar mass of NaOH. So 23 plus 16 plus 1 is equal to 40. Number of mass is equal to number of moles times molar mass. So 1.2525 times 10 to the negative 2 multiplies by 40. Zero 0.0501 gram. So the X that they dissolved was this mass of sodium hydroxide. Any question? Do we have any question?
No, miss.
All right, so that's a similar question to the one we did earlier. All right, so we're gonna find another one to do. The titration question we're going to do now is a redox. So we're going to be looking on a redox titration. So using this to calculate the percentage of iron in a salt sample. An experiment was carried out to determine the percentage of iron in a salt sample. 0.50 grams of the 50 grams sample of iron salt was placed in a conical flask. So of this, we want to determine how much of it is the actual iron. To it, 25 ml of dilute sulfuric acid was added. So they're adding acid, and then they added 10 ml of phosphoric acid. Then they added 8 drops of indicator. The contents of the flask were mixed and titrated against 0.02 moles per dm cube solution of potassium dichromate. So my standard solution is potassium dichromate, and its concentration is 0.02. So you're going to write that down, because somewhere in the question, they're going to ask me to calculate the number of moles of sodium hydroxide used. So this is the concentration of potassium dichromate used, sorry. So the concentration is 0.02 mole per dm cube. So I'm writing it there. All right. Until the endpoint was reached, the ionic equation for the reaction is given below. So I have 1 mole of dichromate ions reacting with 6 moles of iron 2 salt, 14 moles of hydrogen ions, 2 moles of dichromate, Cr3 plus, chromium 3 plus ions are formed, and 7 moles of water. Figure 1 shows the burette reading of the initial and final volumes of the titration. I'm going to zoom in so you can read them off. What's the final reading for the first titration? So we know we're going down by 1. So we're increasing in the direction there. We're going down by 1. 1 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 divided by 10, I'm going down by 0.1. So this reading here doesn't sit on my meniscus. The meniscus does not sit on my graduation reading, so I'll have to estimate this one. So it's midway between 21.9 and 22. So what's my final reading there? .95. We're clear how we got that?
Yes, miss.
And then this is 2.00, because everything needs to be read to 2 decimal place. Then for the next one, so it's not on my 22. Is it on my 22? Let's rub out this. So the bottom of the meniscus for this is not on the 22 mark. So what's the reading here?
21.85.
21.85 initial.
2.85.
1.85. So I get 1.85.
Yes, ma'am.
Remember, that's why you look on where the direction it's increasing from. Next one, 19.50, and the initial is 1.50. Clear?
Yes, miss.
List the apparatus that would be necessary to carry out the experiment. What are the apparatus we use to carry out a titration experiment?
A pipette.
Burette.
Now we need a pipette, burette,
Conical flask.
conical flask,
Judge.
Indicator.
dropper, apparatus. So that's a material. I need a retort stand. And they need a funnel to fill the burette. Clear?
Yes, ma'am.
Yes, miss.
So let me put in my values. So into 1.85. All right. Then it says use an asterisk to indicate the titration data that should be used. to obtain the average volume. So my asterisk would go here and here. Then it says, hence calculate the average volume of potassium dichromate using the experiment and record the values to 2 decimal places. So it would be 19.95 plus 20.00 divided by 2, which is 19.98 centimeters cubed. Using the information from C2, calculate the number of moles of potassium dichromate used in the experiment. Calculate the number of moles of potassium dichromate used in the experiment. So we have the concentration, number of moles is equal to concentration times volume. Concentration is 0.020 moles per dm cube divided by 19.98 over 1000. We're doing this step to convert volume from centimeters cubed to dm cube. Anybody have an answer for me?
Miss 3.996 times 10 to the negative 4.
3.96 times 10 to the negative 4 mole.
996, Miss.
Why am I not have 996? Oh, I missed something. When me I divided by 9, it's 996. Okay. From the equation given in page 4, determine the number of moles of iron that reacts with 1 mole of dichromate. So it says from the balance equation, 1 mole of dichromate reacts with 6 mole of Fe2 plus a 6. Let's go check. Six moles of Fe. So the mole ratio should be 1 to 6. Then it says calculate the number of moles of iron in the sample. So we're going to use the mole ratio. 1 mole of dichromate ions reacts with 1 mole, 6 mole of Fe2 plus. So therefore, the number of moles of dichromate which reacted 3.996 times 10 to the negative 4 is equal to X. So cross multiply 3.996 times 10 to the negative 4 multiply by 6 equal 1 times X, which is X. What we got?
Well, 2.3976 times 10 to the negative 3, Miss.
Okay. So
Yes,
that's
miss.
iron. So they want to know, find out the mass of iron in the sample. Number of moles is equal to mass over molar mass. So to find the mass, it would be number of moles times molar mass. 2.3976 times 10 to the negative 3 multiplied by the molar mass, which is 55.8. I got 0.133. How much? So it's 3 decimal place in the grams of iron that they gave. So I'm gonna round this off to 1.34 grams of Fe. And then the last question says calculate the mass of iron in the sample. So the sample of iron salt was 0.05. So the mass of iron divided by the total mass of the iron salt multiplied by 100. My answer is 6.8%, 26.8%. Clear?
Yes, Miss.
All right, so that is it. Redox. We have an next redox question, but I don't want to do that. I want to do this question. All right, so here is a thermometric titration question. It's not much titration, it's more thermometric, but it has some moles calculation there. Girl, I'm gonna tell us let me go teach. She gone from the road with her daddy. Me gone left her. Me I teach my class. So all when me free, me still have class later. All right, so the concentration. Okay, this is it. So this is January 2021, if I remember correctly. So the concentration of sodium hydroxide in grams per dm cube was determined via a method of thermometric titration with a strong acid. So the question didn't ask us what a strong acid is, but I want to know the answer for this. A strong acid. What is a strong acid? Ionizes fully when dissolved in water. So when strong acid is placed in water, it fully ionizes when it dissolves in water. Weak acid only partially ionized when dissolved in water. So the following procedure was used: transfer 25 centimeters cube of sodium hydroxide solution, known concentration in a styrofoam cup of unknown concentration. So this is the unknown. So that's the one we pipette in. Then we're going to take the initial temperature of the solution. Then we're going to add 5 centimeters cube of H2SO4. And its molarity is 0.10 moles per dm cube from the burette to the cup. Immediately stir the mixture and record its temperature. Repeat the procedure, adding 5 centimeters cube aqueous of H2SO4 until a total of 30 centimeters cube of H2SO4, 0.1 mole per dm cube or 0.1 molar is added. Figure 1 shows the thermometer reading for the acid-base titration after the addition of 5 centimeters cube of the solutions. So first, we look at where we are increasing from. We're increasing from top to bottom. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So between 27 and 10, we're moving by 1 and we're dividing by 10 spaces. So each space is 0.1. So this thermometer reads 0.1 and it reads increasing from bottom to top. What's the reading? So it reads different from a burette. What's the reading? Please.
27.5.
27 point what? So 1, 2, 3, 4, 5. So we have 27.5. 15 is what?
33.4.
33.4. And then 28 is what?
28.9.
Using the thermometer reading in figure 1 on page 5, complete table 5 by recording the temperature for the additional 5, 15, and 25. So we read them off, going to add them to the table. So 27.5. And then 15 is 33.4. Somebody take this picture for me, please. When I'm finished, 33.4, 25 is 28.9, and 30 is 26. So we notice that temperature is increasing and then it starts to decrease. Somebody take this picture for me, please. Let me know when somebody have it.
Yes, Miss.
So I'm running straight to plotting the graph. I'll go back to the rest of the questions. So again, we'll check what we're going up by on each axis. So we're going up by 1. From here to here is 1. 1 divided by 5 is 0.2 on the y-axis. On the x-axis now, we are going up by 2. 2 divided by 4 is going to be 2 divided by 5, sorry, is going to be 0.4. All right, let's go. So read for me, please, the first one. First volume.
Miss, the first value was 0 to 25 point
0 to what?
25.0.
0 to 25 point what?
0.
2.
0 to 25.
All right, next.
5 to 27.5.
5 would be midway between here. So 5 is going to be 2.5 box from 4, because this is 4.4, 4.8, 5.2. So midway there. What are plotting?
27.5.
27.5,
Yes, Miss.
which would be midway here. 10 is
Then
what?
10, 30.5.
So 30.5. No, it's only
15,
10. Hold on.
33.4.
30 what?
33.4.
That's a 15.
Yes, Miss.
So 15 are gonna be the graph. I need to zoom in a little way more. So 15 is going to be what?
33.4.
33.4.
Next one,
Yeah, 20.
20 is 32.5.
32.5.
Yes, Miss.
25.
28.9.
25, 28.9.
Then 30 is 26.
30 is what?
30 is 26.
All right, so I plot the graph. So let's read what I missed. So it says using the axis provided on figure 2 on page 7, plot the graph of temperature against volume. Then it says draw 2 lines of best fit through the points on the graph, one where the temperature is increasing and one where the temperature is decreasing. That look like it for me. No hurry. I'm gonna draw this now. Remember, say my ruler, not ruler in. All right. So where the two lines intersect, that is where my volume of what my volume of sulfuric acid would be. So because my line are lining, let's just read it off. So it's the first small box after 16. So it's the first small box after 16. So it's going to be, so on the y-axis, I'm going up by 0.4. So the volume of H2SO4 would be 16.4. All right. So right here is where both lines intersect. So I draw a broken line there to read off.
Excuse me, Miss. Miss, I know why wouldn't Miss why wouldn't I use a curve, Miss?
Because then tell me if you draw two line of best fit.
Oh, maybe
And thermometric titration is not all the time you get a curve. So even when we get the curve, we draw the two line of best fit too. It's a balance equation. No, we're not done. Then it says the endpoints of the reaction. The volume is 26.4. So here's where it says draw two lines of best fit. Distinguish between strong acid and weak acid. So we had already answered that question. What was the answer?
Miss strong acids, Miss strong acids, all the hydrogen are fully dissolved in the solution, while weak acids are partially dissolved.
Partially ionizes.
Yes, Miss.
Fully ionizes when dissolved. It produces a large concentration of H plus ions, while weak acid produces a small concentration of H plus ions. It's a balanced chemical equation. I same thing we've been writing. It was a state symbol, but me just a practice. So when they not ask me, when they actually ask me, me stay ready.
that may always be to
Number of moles of H2SO4 used. So we know the volume of H2SO4 is 16.4. So the volume, so we're gonna go back to get the concentration. So the concentration of H2SO4 is 1 molar, 0.1 molar. So the number of moles of H2SO4 is equal to concentration times volume in dm cubed, so 0.1 over 16.4 divided by 1000. (1.64 times 10 to the 3), that's what we get?
Yes, miss.
Negative 3, sorry. Calculate the number of moles of NaOH in 25. So do we use the volume here? Do we use the volume here? Do we use the volume of sodium hydroxide here? No, we don't use the volume. What do we use? Mole ratio 1 mole of H2SO4 reacts with 2 moles of NaOH. Therefore, 1.64 times 10 to the negative 3 mole of H2SO4 reacts with X mole, cross multiply. 1.64 times 10 to the negative 3 times 2 is equal to 1 times X, which is 1X. So my answer for X, 1X is the same as X, multiplied by 2 is equal to 3.28 times 10 to the negative 3. Negative 3 mole NaOH. So now they want us to find the concentration. Concentration is equal to number of moles divided by volume. Volume must be in dm cube. So it is number of mole, 3.38 times 28, why I keep saying 38, times 10 to the negative 3. The volume that we're using is the volume up here, the 25, divide by, 25 over 1000. So this is primary school math. We keep the number, then we change the sign, and then we flip. Times 1000 divide by 25. Mathematicians, and I get 0.1325. 0.1312, sorry.
Yes, miss.
All right, so we still keep the formula where it says divide by the volume in dm cube. So I divide by that, but when I divide in by a decimal, I have to flip this, change the sign, and flip the decimal. Calculate the concentration of sodium hydroxide in moles. Number of moles is equal to mass over molar mass. So mass is equal to number of moles times molar mass equals the mass. So I'm at, what am I there? 0.1312 multiplied by 40.
5.248, miss.
5.24. 5.248 grams. State whether the reaction took place in the styrofoam cup was exothermic or endothermic.
Did it Was it a heat loss or a heat gain? Miss, can I go back to the question?
What do you mean? There's a temperature increase.
Yeah, that's why I said go back so we can like see.
Neutralization reaction exothermic.
Yes, miss, because of the
Never know what I say now. I'm not paying no mind. Exothermic as temperature increase. Stay one safety precaution that should be taken during the experiment. Fill the burette with a funnel. All right, so that's a thermometric titration there. We said we would end at 7, so I'm going to end this recording. There are 2 more. All right, so rates